In this video, we are going to solve a simple Thermodynamics 1 problem using our water tables. So let's get started. A vessel is partitioned into two parts. The left side is filled with 0.2615 pound mass of water at 30 psia to fill the 4 feet cubed left chamber. The right chamber is initially evacuated and twice the size of the left. The partition is removed and the water is allowed to mix uniformly to reach a final temperature of 40 degrees Fahrenheit. What is the final pressure of the system? Is there quality? And if so, what is it? So I'm going to go ahead. So there's two states here. So I would say like the mass when it's just A is equal to 0.2615 pounds. The pressure initially is 30 psia, and our volume on the A side of the chamber is 4 feet cubed. Alrighty, what else do we know? We know that the chamber on the right is initially evacuated and twice the size of the left, and then the partition is removed. So the volume, so the volume of B is 2 times the volume of A, and then the value of AB, so chamber A and plus chamber B, right? Because the partition is being removed, allowing water to like penetrate and mix uniformly, would be the volume of A on the A side plus the volume of the B side. Alrighty. The mass of A and B, so when the partition is removed, is still going to be 0.2615 because it's a closed system. There's no mass coming in or out. Just because you give it more space to move around doesn't change the amount of mass that it has. And the pressure, let's see. The pressure is of AB, that's what we're trying to find, our final pressure. Our temperature at the end, so our AB temperature when they're allowed to mix, is 40 degrees Fahrenheit. Alrighty. So we kind of need a plan. We need to figure out how the heck am I going to determine the pressure when they two mix. So in order to use thermodynamic tables, you need two values. So usually like either like pressure, temperature, specific volume, anything that you can find on the saturation tables. So in this case, I'm given temperature. Great. I need one more value. Mass isn't going to cut it. However, what we can get or what we can find on our thermodynamic tables is our specific volume. So let's go ahead and try finding the specific volume. So our first thing in our plan is to find the specific volume of AB, which is going to be the volume of AB over the mass of AB. So we know the mass of AB, however, we don't know the volume of AB, but we can figure out the volume of AB using these two equations right there. So we'll go ahead and do that. Second part of the plan is to we're going to determine state with the specific volume and the final temperature. And then the third part is going to be to determine the quality, right? If it's a saturated mixture. And our formula for quality is this guy right here. Alright, so let's do the first part of our plan. So find the specific volume of AB. I'm going to need my volume of AB. So we know that VA is equal to 4 feet cubed, right? So I'm going to go ahead and plug that in. 2 times the 4 feet cubed is going to give us that the volume of B is 8 feet cubed. And then we plug those numbers into to find the volume of AB combined. So VA, or volume of A, is 4, the volume of B is 8. So our volume of A and B combined is going to be 12 feet cubed. Great. So now let's go ahead and find the specific volume of AB. Again, that's the equation. We plug the things that we know. 12 feet cubed over 0.2615 pounds. And we get 45.889 feet cubed per pound. Now that we have our specific volume of 45.889 feet cubed per pound mass, as well as our final temperature of 40 degrees Fahrenheit, we can look them up in our tables. So we're going to go ahead and go to table 6.1, properties of saturated water. And we are going to the table 6.1 because that contains our English units. And we're talking about pounds and feet cubed, so we're going to be looking at English units, not SI units. Okay. When you look it up, our tables look like this. I don't know how yours looks, but this is how mine look at the end of my textbook. And we're going to look for our temperature at 40 degrees Fahrenheit. Alrighty? So I'm going to locate 40 degrees Fahrenheit, and also make sure that you're looking at the water tables and not propane or any other one, please. And so I'm going to go ahead and circle it. And since we're going to go ahead and compare the saturated liquid, the liquid vapor and vapor specific volume values, we're going to compare it to our specific volume value. So I'm going to compare it to this guy and this guy. Our specific volume value lands in between both of them. Right, so the saturated liquid volume is 0.01602 feet cubed per pound mass, and the specific volume of the saturated vapor of water at 40 degrees Fahrenheit is 2,445.0873 feet cubed per pound mole. And our specific volume is 45.889 feet cubed per pound mass. Since our specific volume value lands in between the saturated liquid and saturated vapor specific volume value, that means that it is a saturated mixture. saturated mixture. If you don't remember why, go ahead and look back at some of my past videos where I have a cheat sheet as to how to know when it's saturated or when it's superheated or compressed liquid. And let's go ahead and show why using our PV diagram. So let's say, we looked up the temperature. We looked up the temperature at 40 degrees Fahrenheit, right? And we looked up the saturated liquid value, which was this, whatever, and then we looked up the saturated vapor value, and we saw that ours landed between those two numbers. So that means, I'm going to go ahead and put it there. I'm not sure if it's going to go there, but it means it's under the dome. And if it's under the dome, it's a saturated mixture. If it's over here on this side, then that means it's a compressed liquid. And if it lands over here, that means it's superheated. So let's continue. We found out that it's a saturated mixture. However, we're still not done. Because if it's a saturated mixture, we have to find out its quality. So I'm going to go ahead and write down the formula for quality. Our specific volume is 45.889 minus our specific volume for saturated liquid, which was 0.01602, divided by our specific liquid vapor value, which is over here, which is this one. Again, all of the values I'm using are from our table. So 2445.0713, and we get that the quality is equal to 0.0188. After you plug it into the calculator, you see that this is what the quality is equal to. Which means 1.88% of the substance is vapor, and the rest is liquid. When your substance is a saturated mixture, it means that liquid and vapor are coexisting. And the quality tells you how much of it is in vapor form. And that's going to be it for today's video. I hope you learned something, and good luck with your studies.